Dr. Aniket Sule is an associate professor in Homeo Bhabha Center for Science Education of TIFR, Mumbai. He is the General Secretary of International Olympiad on Astronomy and Astrophysics, and he is the chair of Astronomical Society of India Public Outreach and Education Committee and National Astronomy Education Committee (NAEC) India. He has his topic of PhD was computational solar physics, and his current research interests his history of astronomy in India, astronomy education, and mathematics education. So I welcome Dr. Aniket Sule for this FDP program, for this session, and I request him to deliver his talk.
Thanks, Jayant. But what I would recommend first is, I think participants have been listening to Mahesh's lecture for some time.
Yeah.
So if they want to take a 2-3 minutes bathroom break, we can start 11:40.
Yeah, we can start 11:40. Yes.
So if people want to have a bathroom break, they can quickly go.
Yeah. Sure.
I will share my screen in the meanwhile.
Yeah, sure. It's visible. Perfect.
Yes. So I will start at 11:40 as per my watch. And while I'm presenting, I may not be able to see the screen. If you people have any questions in between, you can stop me by just speaking. I may not be able to see your messages on the chat. Or maybe you post messages on the chat and then Jayant can tell me if there are any questions.
Yeah, I will inform you.
Okay, so let me start. The topic which I have chosen is distance measurement methods in astronomy. What I will do is I will start from the smaller scales in astronomy, that is within our solar system, and then slowly start going outwards. And then at the end we will. So first we start with distances to the planets. Historically, even before Kepler, there were methods by which people could estimate the distance ratios between the planets. For example, once Copernicus gave heliocentric system, then it was clear that this heliocentric model can be used to get ratios of distances. For inner planets, we use what we call as the elongation, maximum elongation of Mercury and Venus. That is, you check what is the maximum angle Mercury or Venus makes with, so the angle planet, Earth, Sun, that angle is called elongation, planet, Earth, Sun. And what is the maximum elongation that is made? That will give you the distance to inner planet. For outer planets, that is Mars, Jupiter, Saturn, and all those, what people did was they found, as seen from Earth, how many days elapse between the opposition of planet to the quadrature of the planet. What you mean by these terms? Opposition means at sunset the planet is just rising, so it is opposite to the sun. Quadrature means at sunset the planet is just overhead, so it is on the meridian. So the angle between planet Earth Sun angle is exactly 90 degrees. So how many days pass between opposition and quadrature is what they found out, and use that to find period for outer planets. So this data was already available to Kepler, and then Kepler used this data to give this his third law. At the time, gravitation was not known, so he could not have derived the third law, but he, by observational evidence which he had, he already knew the ratio of distances, and he could measure the periods of the planets, heliocentric periods. So he could derive the relation that T square is proportional to A cube, and if you take T in years and A in AU, that is this between Earth and Sun to be 1 AU, then you just simply get T square is equal to A cube. So that is how Kepler could derive this relation. So we knew distances in AUs from just shortly after Copernicus. So sometime nearly 500 years back, we knew distances in AU, but we did not know the distances in kilometers. For that, we had to actually get a reliable distance. We had to actually wait for radars to come by, and then during Venus transit, we could, during the Mercury transit, the distance to Mercury could be accurately measured by radar in absolute terms, and then we could say that okay, this much AU corresponds to this many kilometers. That is how we determine the distance 1 AU in kilometers. Then other method which is used, which is probably Mahesh mentioned in his lecture, I joined a bit late, is observing the inner planet transiting from two different latitudes, but from two places which are on different latitudes but same longitude. So this method was proposed long back. In 1663, Gregory first proposed this method. That if we can do that, if we can do a simultaneous observation of transit from two places with different latitudes but same longitudes, then what we will see is the path of Sun or path of the inner planet on surface of Sun will appear to be slightly different. So in the right side image, the one latitude you will see path B, other latitude you will see path D, and if we can measure these differences, how much is the difference between the projected path on the Sun, then we can accurately estimate the distance of that inner planet during the transit. And that is how it was actually measured during transit of Mercury by so Halley also independently subsequently for the transit of Mercury in 1691 and 1716, this method was used. Then 1761 transit of Venus, again this method was used to measure distances to Venus and Mercury. For distances to nearby stars, what we use is what we call as parallax method. We teach parallax in school, in colleges, also in high school. So what typically happens is, for if we look at a nearby object on the background of some distant screens or distant objects, then as we change our position, it appears that the position of nearby object has changed. This many examples are given in our textbook. Like if you're traveling in a train and if we look at some cow in nearby field and look at it with respect to the background of some distant mountains, then it will appear that the cow's position with respect to the background has changed. So earlier cow was behind in front of a certain mountain, then after some time as train moves ahead, the cow is not in front of that mountain, but it is the background of cow has changed. So same thing happens with stars. In this image, what we see is, if as Earth goes around the sun, then two different locations, opposite locations, June and December. If you look at nearby star, then you can see the animation here. June, the bigger star in June, the bottom panel, and December, it will appear to have moved. So that is how the motion with
animation is not visible.
Animation is not visible.
No.
I'm just going back and forth between in the bottom panel. It is not actually animation.
Okay.
I'm not. So just
yeah. Now it was there. Yeah. Okay. Fine. Yes.
Yeah. Okay. So so this change in the position of the nearby star we can measure with respect to background stars, and that will give us the angle that star subtends to Earth's orbit, and that will give us the distance, because we already know 180. So first parallax measurement happened for a star called 61 Cygni, which is quite nearby star, and it was done by Bessel. And obviously the highest parallax will be for the nearest star. So Alpha Centauri, they were not the main observational areas for the astronomers in Europe. So the parallel.
So your voice is breaking, sir.
Before measuring,
Your voice is breaking.
all the parallaxes, they did not know that steep parameter. Sorry, what
Sir, I
did you
have
say?
a question.
Your voice is breaking.
Yeah.
Yeah.
Actually, sir, I am having a question over
Yeah.
here. You have
Yes.
talked about the parallax method. Do the axial rotation of the Earth
Hello.
affect in the positions?
Axial rotation will affect the position, but what we typically see here in this diagram, when the Earth changes the position by 2 astronomical units, that is nearly 10 raised to 12 kilometers,
2 weeks.
or 10 raised to 11, you can say, or 3 raised to 11 meters, not kilometers, meters. So when you change the Earth's position by that much distance, then you see a change in the position of the nearest star by less than 1 arc second.
Less
So
than one?
if you less than 1 arc second, that is 1 by 3600th part of a degree.
Yeah.
So 1 degree is 60 arc minutes, 1 arc minute is 60 arc seconds. So 1 degree is 3600 arc seconds.
Fine.
So when Earth changes position by 2 AU, then nearest star's position changes by less than 1 arc second. So if you just rotate at its own place, then the distance is only changing by 12,000 kilometers. The difference in the position, even for the nearest star, will be so small that it would not be measurable by most historical telescopes. Obviously, the most modern telescopes would are capable of measuring these small differences, but those are professional modern telescopes. So if you look at the historical measurements, or astronomers can do presently, they will not be able to measure this difference.
Thank you, sir.
So by measuring parallax, we can now figure out these are the stars which are closest to the sun. So here, this diagram, what they have shown is direction is shown by those in the blue circle, blue plane, and then if the stars are above or below the solar plane, then they are shown accordingly at that distance, so at such height and so on. So 61 Cygni you can see on the right. It is also within the 10 light year distance, and obviously Alpha Centauri is in less than 5 light year circle, and you can see all the stars up to 15 light years. Many of the stars you may not even have heard about because some of them are very small stars, but some stars obviously you would have heard: Alpha Centauri, Proxima Centauri, Sirius, Procyon, then Epsilon Indi. These are the stars which Tau Ceti. These are stars which are visible to naked eye. So these stars obviously we would have seen if you are used to looking at the sky, a night sky. Okay. Then we move to now. So these methods typically are useful for nearby stars. As I said that until we launched a satellite called Hipparcos, which was about 20 years back maybe, we did not have very good instruments to accurately measure parallax in like at milliarc second level and things like that. So our measurements were approximate. So now we can do that much better. There is Hipparcos, there is Gaia. They have done this fantastic surveys. But since we inherently had historical limitations on these methods, people devised many more ideas how to get a fair estimate, and everybody was happy with a fair estimate. We wanted to know whether the star is 5 light years away or 50 light years away or 500 light years away. It did not really matter if it is 5 or 5.1 or 4.9. So to get that fair estimate of star distance, we devised multiple methods. So one such method is secular parallax. So what we do in secular parallax is we take all the stars around the sun. Right, so all the stars in stellar neighborhood. We say that okay, all these stars on an average should be going around the center of the galaxy. There may be some small additional random motions, but overall they should be going towards the center of the galaxy. So if we draw circular shells around sun, then their average velocity should be towards same direction. So if you take these average different shells and plot their angular velocity with respect to sun and the angle made with respect to the direction of sun's motion, then we see that they follow certain trend lines. Like green shell will have the green trend line on the right side, red shell will have the red trend line, So that will give you the average angular velocity of these shells, and then that based on that we can get estimate on which stars may belong to which shell. Again, this is a very approximate method, but in the old days this was one of the method which was used. Then for stars which are slightly further away, not the solar neighborhood, but further in the galaxy, we use something called kinematic distance. So in this diagram which is shown here, the sun is going around the center of the galaxy, that is the outer orbit. If you take some blue star, which is in another circle going around the center of galaxy inside a shell, so it also has some velocity. Since sun is in the flat part of the rotation curve of the galaxy, the velocities are same v0 in both cases, the nearby star as well as further star. So as seen from sun, we can resolve those velocities as Vr and V theta. So that by measuring how much is the Vr per component of that star, we can estimate how far that star will be. There will be two stars. Blue, for example, the blue star and red star will have same Vr, but different directions of V theta. So we have to measure the Vr and we have to measure the direction of V theta to decide whether it is the star is at blue position or the red position. So the kinematic distance will also give you distances to the stars. Then from stars we go to other objects in the galaxy. There is something called planetary nebulae. So for planetary nebulae, what happens is, especially for young planetary nebulae, they keep expanding in size. The stars which have become planetary nebulae in last like couple of thousand years, we can measure their rate of expansion, like the angular size of the star of the nebula as it grows, and at the same time, if there is some gas. So most of these nebulae expand in a spherically symmetric way, almost spherically symmetric way. So there is some gas also coming towards us, some gas going away from us. So from that gas, we can measure the Doppler shift in the spectral line. So we know what is the absolute radial velocity. By measuring the changing size, we know what is the angular expansion velocity. We can combine both these to find distance to that nebula, assuming that the angular expansion velocity is caused by the same linear velocity which we are measuring in the radial direction. Obviously, if Vr is not equal to the sideways velocity, then there will be systematic errors. But usually, as I said, they are expanding in almost spherically symmetric way. So this method works to give fine. There is something called moving cluster method, which actually works for only few open clusters close to us, but nonetheless it was an interesting method. So for nearby clusters, what they do is they plot the direction of motion of all the stars in that cluster, and they figure out that all these stars, they seem to move towards same convergence point. And then once they figure that out and subtract that velocity, what they will get is just the remaining component of the star velocities are just due to the random motion within the cluster. And then that way we can determine the size of the cluster, which at plus the radial velocities of these stars will tell us what is the magnitude of velocities. By measuring size of cluster, we know what is the angular separation between the maximum stars, so we can determine the size of cluster, absolute size of cluster, and hence we can determine the distance. Another method which is used not just within our galaxy, but also uh, for nearby dwarf galaxies like large Magellanic Cloud and small Magellanic Cloud, is what we call as light echo. So in this picture, if you look at the top panel, what on the right side there is a spherical shell, which is a spherical nebula, which is result of a supernova, uh, which happened in 1987. So this supernova in Large Magellanic Cloud is famous as 1987 A supernova. Now this supernova caused a shock wave, and that shock wave is traveling through the galaxy. In February 94, what they saw, that a particular region of this galaxy, the Large Magellanic Cloud, was getting brightened because of the shock which reached there. On in the top panel, you can see almost vertical bright structure on the left side. After another year, they found the supernova is still on the right side, but the shock position had changed. So earlier in this February 94 picture, the top left part, you can see in the middle of shock there is a bright star, and then in March 95 picture, that bright star has actually is well away from the region which has become bright. So as the shock travels through the galaxy, different parts are get that shock wave, and they get brightened. This is light echo of the supernova, and you can measure this change in the light echo to measure estimate distance of this galaxy. By how much in how much time, how much this shock has traveled, because we know the radial velocity of the gas, we can estimate that. Same thing we can do inside the galaxy as well. So this is a star called V838 Monocerotis. This was also giving away a big spherical shell, and we could see the light echo of this shock wave through May to December of 2002, and that light echo gives us, again, by measuring radial velocity and comparing with light echo, we can compare we can measure the distance to this star. Okay, then we go to something called binary stars. Stars, there are dual methods. There are some stars which we can clearly see separate with naked eye, like Mizar star. Mizar has Mizar A and Mizar B, and we can also measure the spectra of both the stars independently. In the spectral lines, what we see is, as the stars go around each other, the spectral lines tend to, from both the stars which get combined on a single spectrum, they separate and then keep merging again as per the motion of the star. And that movement is what we call as Doppler splitting. For few as the stars are beside each other, then the splitting is maximum, as we see. And when the stars are in the same line of sight as we see, then there is no splitting. So using the Doppler splitting, how much splitting is happening, we can measure the velocities of the stars in their orbit. And since we can see those stars separately, we can measure the maximum angular separation between them. So we know what is the distance between the two stars, two components of that binary star. So using that, again by using Kepler's law, we can measure the absolute size of their orbit, and hence we can measure get their distance. And this method proposed about 80 years back, called Bade-Vasily method. So what these two scientists showed, that if you have a star which is pulsating, expanding and contracting, then you can measure the flux and color of the star at extremes. So that will give you the ratio of color, means so astronomers define color as the difference between magnitudes in two different bands. So in the equation, it shows as B minus V1 and B minus V2. Flux is given by F1 and F2. So the radius ratio can be will be given by that equation. And then if you measure the radial velocity and period of pulsation, then we can do R2 minus R1. It will be given by velocity times T2 minus T1. Use these two equations to find the absolute radius of the star, and then d, the distance will be just radius divided by the angular size. If you have spectroscopic eclipsing binaries, that is the stars which are eclipsing each other while they are going around each other, then again you can measure the topological splitting and measure the ratio of radii from eclipses, and use those two equations to find a distance. Another approximate method which is very common earlier is, what they do is they simply measure magnitude of the star, apparent magnitude. They find the color of the star. From color they know, okay, if this star is going to be on main sequence, for this color the main sequence is somewhere here. So use that to find the absolute magnitude or get an estimate of absolute magnitude, and then use apparent magnitude and absolute magnitude together to find the distance, roughly distance of the star. So okay, then we come to a type of variable stars called RR-Lyry variables. So historically, what was believed that all RR-Lyry variable stars have same absolute magnitude, and that is why if you find some RR-Lyry variable star and you know its apparent magnitude by simple measurement, the absolute magnitude is anyway going to be same. So later that directly gives you so the absolute magnitude of RR-Lyry variable and apparent magnitude will give you the distance. Now recently, last 10 years or so, there have been some research which says that it is not exactly same magnitude for RR-Lyry variables. There may be, if you go to some other galaxies, it may be slightly different than what we see in Milky Way, and that is why this is less reliable than what we thought it is. The other two stars which you see there are the two groups. One is called classical Cephids, one is called type 2 Cephids. So these stars, the Cephid type stars, they show a very clear relation between their period of pulsation or period of their variability and the absolute magnitude. So once you know which type of Cephid it is, and that can be determined based on the type of curve, the intensity curve which this variability follows, we can put them on this by measuring period. That will give you the absolute magnitude, and that will tell us exactly how far these stars are. This is called period luminosity relation of Cephids. Again, it may be slightly affected by the chemical abundances in those stars, but slightly. So within a band, you should be okay. Then there is another approximate method where it is believed that the brightest planetary nebula in each galaxy has roughly same brightness, because planetary nebulae are formed by death of certain type of stars, and beyond a certain size you don't get a planetary nebula. So it is reasonable to make that assumption. But again, that theory is behind it is not properly understood. So there is a strong correlation right now, but we don't exactly know the physical reason behind it. Similarly, it is also believed that the most massive star in the galaxy will be of roughly same brightness. There will be very few stars of that type. So if you can find individual stars, we would know their absolute magnitude, and by measuring the apparent magnitude, we can get the distance to that galaxy. So now we're going outside our Milky Way. We are going to measure distances in other galaxies. Similarly, brightest H2 region again is believed to be same. Then this is more concrete. So if you take a very detailed image of a distant galaxy, then the number of stars per pixel will change depending on the surface of on the distance of the galaxy. So distant galaxy, in each pixel you will get large number of stars. So that is why statistical fluctuation from pixel to pixel will be smaller. Whereas if you take a nearby galaxy, you will see more fluctuation as you go from one pixel to next. Okay. Next, Tully-Fisher relation. Again, these two are astronomers. So Tully-Fisher relation, what they say is, if you measure the rotational velocity of a galaxy, it is correlated to the total luminosity of the galaxy. So luminosity of the galaxy is proportional to rotational velocity to the fourth power, and this is also seen to be valid in almost all galaxies. So Tully-Fisher relation will tell you the absolute luminosity of the galaxy, and by measuring the apparent luminosity, we can measure the distance to the galaxy. Next, this is one of the most important methods in large distances. So that's supernovae of different types. So there's one thing, or one particular type of supernova called supernova 1A. That happens when a white dwarf accretes too much matter from its binary companion and crosses the Chandrasekhar limit. When that happens, it becomes supernova, and magnitude of that supernova is going to be absolute magnitude is always going to be minus 19.3 with some error margin. And once we know that, we can calibrate. If we see a type 1 supernova in any galaxy, we can measure its apparent magnitude, and that will tell us the distance to the. So here are light curves. That is how the light changes, total light changes for different supernovae. The relative brightness, as you can see, there is some variation. So the light curves don't exactly match, but what the astronomers who got the 2011 Nobel Prize, what they showed was, although these light curves appear to be different, we can apply a proper calibration and they can be matched exactly. So by doing this calibration, all these light curves exactly match with each other, and hence we can use supernova 1A as a very standardized way to measure distances between galaxies. Then there is Faber-Jackson relation. Weber-Jackson relation tells you that the stellar velocity dispersion in elliptical galaxies is again proportional to the luminosity. So the dispersion raised to 4 is proportional to the luminosity. Again, that will give you the absolute luminosity of the galaxy. So in cosmology, we see often a general relativistic effect, what we call as lensing of light. So if there is some source that on the top, in the top panel, suppose there is a source which is shown in yellow color on the left side. The light from that source is traveling towards us, which is the green sphere on the right side. But in between there is some galaxy. Then what happens is we see the light bent because of the gravity of that intermediate object, and instead of seeing at one source, we may see a full ring, what we call as Einstein ring, or in the lower panel we can see that we may not see a full ring, but we only see two or three images. Of the source. So these are some examples of Einstein rings. The central yellow object is the intermediate object, and around that the blue things which you can see are the background sources which have been lensed and have become this weird shaped or half ring or partial ring type of galaxies. So how we use this gravitational lensing to measure distances? So when you have a gravitational lens and there is a source which is not exactly behind the center of the intermediate object but slightly off center, then we see the two images slightly differently. And if that background source is a quasar, then typically quasar emissions they keep fluctuating over time. So we exactly know what is the time delay between first part of the second stage will give us the distance to the lens, that is the distance to the source, which is ds, as shown in the equation, where theta is the size of that. Theta is what we call as impact parameter, that is how close to the intermediate object the light ray is passing, and beta is the off-center angle of the source with respect to the line joining intermediate object and the observer. Yeah, so this is shown theta and beta. Okay. So in astronomy, in cosmology mainly, not in astronomy, in cosmology we define redshift Z is like that. 1 plus Z is lambda of observed divided by lambda emitted. If you want to do relativistic calculations, then that is next formula is shown, which is also the scale factor or size of universe now versus size of universe then. So if you do 1 over 1 plus Z, then that will give you rate of change of the scale factor divided by scale factor. So this will so if you can observe with a light from very distant galaxy, and if we find some spectroscopic lines which are known in our laboratory, so then we can do lambda observed by lambda emitted, which will give you the redshift for that galaxy. Then in 1920s, Hubble found a very interesting correlation between how quickly galaxies are going away from us, that is what we call recessional velocity, and their distance. For that, he used the Cephid variables in those galaxies to find their distances, and he came up with this law, what known as Hubble's law, that velocity is equal to some constant into distance. Now, it is in Hubble's time he thought was constant, and he calculated some value. Now we know it is not exactly constant. We now call it Hubble parameter, but we roughly have fair idea what that constant that parameter value should be. So when Hubble started measuring, he thought that value of constant in the units given, that is kilometers per second per megaparsec, was more than 600, and then different people tried estimating this value over time. So from 1927 till 1975 or something like that, there were only few measurements, and then by 1960s people had already started discussing value 50 and 100. So before 1960, there were many papers which thought the value is above 100, but then after 1960 it was between 50 and 100, and then after 1980 there were too many measurements. If you look at measurements 96 and 2008, there are so many measurements, and mostly between 60 and 80, and slowly converging towards 70. So presently what we have here is, if you look at 2020, there are two possible values. One value based on supernova 1A calculations gives value of roughly 70 kilometers per second per megaparsec. And if you look at something called cosmic microwave background, then it gives value of 67. And if you read astronomy articles presently, this is sometimes called as Hubble tension. That is that two different methods which are not agreeing on Hubble's value. So that is one of the big research areas presently in the astro. So just to summarize, for different distances we use different methods. So for solar system, which is at the bottom, we use direct measurements from Earth's surface. Then for nearby planets, so nearby stars, we started using parallax. Then we went to spectroscopic parallax, then Cephid variables, then novae and supernovae, then galaxy photometry, then galaxy redshift, and so on. So CMBR, I mentioned that there is this cosmic microwave background radiation, CMBR, which is almost equal. Hello.
क्या कर रहे थे?
Is it a question for me?
No, it is not a question. Somebody just I muted it. You can continue.
Okay. So cosmic microwave background radiation is almost uniform coming from all directions, which was known in 1960s. So Penzias and Wilson, when they found it to be almost uniform. If you remove that common component which is shown on the left panel top, if you remove radiation corresponding to 2.728 Kelvin from everything, then at millikelvin level we see this dipole-like structure in the CMBR, which is because of sun's motion in the galaxy. If you remove that component, then we actually see the galaxy coming out in the center, the red part, the third one, at 18 microkelvin level. And if you remove even that galaxy component, which is again known component, then we see CMBR's variations at like these, and these variations tell us about the size of universe at that time. This is the so CMBR, as I said, can be again used. The size scale of these small dots can be used to measure value of Hubble parameter, and that tells us something about the distances of the large at the largest scale. So summarize. First thing we should remember is no science fits everything. For small distances, we have different method. For larger distance, intermediate distances, we have different method. For larger distances, we have another method, and we keep building on this method. So once we know what is the value of 1 AU in kilometers, then we use AUs to find distances in parsec. Once we know what is the value of 1 parsec, then we go to things like Hubble constant and so on. So this kind of cross calibration is always necessary. We have to also check if method 1 is giving one particular answer and method 2 is giving another particular answer. Are they matching with each other? What is it? If there is disagreement, what is the level of disagreement, so on. So this kind of cross calibration is always necessary. That is why we say it is distance ladder, because we keep building on each other. And in all these methods, you should always remember that there will be some errors, and hence when we hold any estimate of distance, you should always ask the question, okay, let us find what is your error bar. Thanks.
Thank you, Aniket, for giving such a wonderful talk, and I am sure all the participants have enjoyed the talk. So this is a question and answer session. If somebody has anything directly to ask to the speaker, you can ask, or you can put it in the one question is there from Preetam Singh. He's in full form of CMBR.
Okay, CMBR stands for Cosmic Microwave Background Radiation. So it is cosmic, that is, it is coming from space. It is seen in the range of microwaves, and it is background radiation. It is coming from all sides. It is not coming from one particular side. So it is cosmic microwave background radiation.
Yeah. Anybody else? Okay, so if there is no other queries, so I thank the speaker for having given time for coming here and delivering the talk. It was very informative and very detailed talk. And if there is any other queries in future also, I think you have joined the WhatsApp group.
Sure.
You can answer it there. Thank you. Thank you.
Sure.